All right, hey everyone, thanks for joining. This is the second episode, I guess, of our dealer training here. This week we're going to concentrate on the 6.7 Powerstroke only, problems and fixes that we have found, and how we fix them. So this will be concentrating on long block, short block and heads. That's it. We're not going to go into any CP4 issues, or Cass might touch on some turbo issues as they affect the rest of the engine, but this is essentially what is affecting the rotating mass in the heads. So we do offer these. Well, actually, let me back up here. So obviously this is for 2011 to current F-Series trucks. There is an info sheet that everyone should have. If anyone does not have this, please let me know. Drop a comment, send me an email, however you want to do it, and I will make sure that you have these info sheets. Just about everything we're going to talk about today, or that Cass is going to talk about today, is in this sheet. The engines are available in our Model C, which is essentially a Ford crate motor with some fixes. It is not a Ford crate motor, it is our motor, but it's just a little bit better than your stock engine would be. The power levels, performance levels go up from there, just based on how you're planning to use the vehicle or how your customer is planning to use it. So we have a daily driver, a workhorse, and then the Cast Watch, which is our race engine. All these engines are available in short block or long block. We also offer the heads separately in a stage 1 or stage 2. We'll get more info. If you want info on that right now, let me know. We'll send you that info. If not, we're going to cover that in a future episode. So on that, I will turn it over to Cass. Cass, whenever you're ready, you're
right.
There you go.
All right, thanks guys. I appreciate everybody jumping on. This is a webinar loosely based on one that I had done before with the Automotive Engine Rebuilders Association, and it was pretty popular. The 6.7 Powerstroke platform is definitely one that has become very, very popular. Keep in mind that Ford actually has kept this current platform longer, and it's kind of hard to even think of it and fathom it, but they've kept it longer than the 7.3. The 7.3 we had it, as far as the direct injection is concerned, it's kept from 94.5 to 2003. So without further ado, we'll introduce you to our webinar here. Let's see if I can get this going. So sorry, bear with me just a second. There we go. This is a cutaway of a 2011 engine. Quickly, we can tell how we know it's a 2011 engine, and I'm kind of going to cover a few things. But I want to cover the entire scope of this engine. And the best way to do that is to understand and put yourself in the mindset of why Ford actually made this engine the way they did. And the purpose of that was because they were coming off the heels of the 2010 crisis of the 6.4 liter. This was a really big problem. Ford, the relationship between International and Ford themselves was pretty strained due to the 6 liter. Tremendous amounts of warranty that they were incurring with a 6 liter. They'd pretty much had it in full up to their necks with the Huey system. If anybody has heard me talk very long about the Huey injection system, I quickly always add, Huey stands for hydraulically actuated, electronically controlled unit injector. But what we refer to it as is helping engines against uneducated installers. The reason why we say that is because you can take that engine, completely run it out of oil, and the engine will shut off on its own. So it's got some built-in safety device, you might say. But the 6.4 was following up to that was changed now from a Huey injection system to a high-pressure common rail. So your injection pressures saw 26,000 pounds of pressure. There are reasons for that. And the reason why I'm kind of going through some of these preliminaries is so that you can understand why the 6.7 was introduced. Because emission standards were becoming more stringent, and more strain, they had to continue to increase the atomization pressure to reduce the amount of hydrocarbons that were being emitted into the combustion chamber. Now, for this to take place, we have to increase rail pressure, and the Siemens pump was able to cap out at about 26,000 pounds. So, with Ford being faced with the issue of their relationship with International, that they were pretty much burnt out with them, and they wanted to be able to keep the quality control in house, Ford did something that they had never done before, and what that was manufacture their own engine in house for this. Now, that was a game changer for them. And there's some really crazy things, and I've said this before, but I'll say it again. If you ever want to see what the cusp of the diesel community is actually doing, if you want to see, as far as engines are concerned, who's the guy on the absolute leading edge, it's 100% Ford Motor Company. Some folks would, argue with that a little bit, but really, it's a hard argument to take because it can be so easily proven. Now, I said they were at the cusp, but I didn't say they were necessarily the best. The reason why I say that is for a couple of reasons. If we kind of go back and we start thinking about some of the things that they introduced long before anybody else, we'll really find out that the first person that had a variable geometry turbocharger on the scene was Ford in 03, quickly followed by the LLY in 04 and a half. If you want to see who the first person actually to use a compacted graphite iron block that was available in a pickup truck, it was Ford Motor Company. If you want to see the first person to run a steel piston in a light duty application in the pickup trucks, it's there again, it's Ford Motor Company. So they really have been the on the leading edge of technology. Problem with it is, as things go, a lot of times being the first, sometimes you run the risk, and most times you run the risk of incurring the most damage getting there. And so Ford was, they were on in 2011 they were combating the LML Duramax. One of the funny things, I guess, the funny story quickly to add was when they first released this engine, they were holding back. They would not release what the horsepower rating was. And they were waiting for GM to make that announcement. They finally did, and Ford bumped it up 15, I think it was about 15 horsepower more just to break that 400 horsepower mark right after that. So there was a lot of competition involved. The diesel industry has always been very, very, very competitive. So a couple of things, though, to understand about this engine, and what we're going to focus on today is what the failures are of this engine. It's important to understand the mindset of the engineer. Now, we're going to do a deep dive in this engine today. This is quite different than the last call we had. I really want to get into the nuts and bolts of this stuff. That's where my heart lies in this. I love the engineering side of it. If you really want to understand where they're coming from, there's one key component, one key thing that they did, two actually. One is take everything that you learned from Ford and your previous pains and woes that you had from Ford Motor Company, from International, through the 6-liter and through the 6.4, and you want to remedy those things. We don't want to carry over and repeat that mistake. The second thing is to introduce a very lightweight diesel engine for what it was. It's a big engine. The thing is really takes up a lot of real estate. However, considering what it is, it's very light when you consider the ratio of mass to weight. And that when they were manufacturing this engine, that was something that was heavy on their mind. Now, I can look back, and it's always easier, as they say, hindsight's 20/20. I can look back and I can tell you, yep, that was a mistake here, that was a mistake there. By trying to lighten certain things up, you really caused yourselves more problems. But like I say, it's a lot easier for me to look back and point fingers. So that being said, let's go ahead and talk about that. Compacted graphite iron block was actually something that had not been done before in the light duty pickup realm. That would increase the weight, decrease the weight of the engine somewhere in the range of 35%, while increasing the strength of it about the same, a little over 40%. So there's a lot of things to be had. Now, we notice these differences as machinists when we go to boring these blocks out and different things like that. We see a major, major difference. Your inserts don't last nearly as long. Now, one of the major problems that we see a lot on the 6-liters, the 7.3s, the 6.4s, anything that's gray cast iron is, it's old technology. Now, it's been in, since the years of the Model T Ford, we're running gray cast iron blocks. However, that's completely changed. So much so now the L5P Duramax is running a compacted graphite iron block as well as is the Cummins. So that's been a game changer. Nobody's going backwards on this. So Ford jumped also into the whole game of aluminum heads. Obviously, Duramax had the first one with it back in 2001, and it worked out well for them. So they thought, we'll just we're going to follow their pattern, because again, keep in mind, lightening up this engine is our biggest concern while meeting emission problems. So they don't just lighten up the engine in the block. They lighten up the engine in the harmonic balancer, which will certainly come to bite them later, and they'll learn that in 2015. They lighten up the cylinder heads by use of the aluminum heads, which will ultimately, through casting problems, will bite them early on in the 11s, and some are all the way through 11. And even we're still discovering some castings that are prone to crack in the intake runners that are problems. And they again will do something that's just radically different, and I'm going to get to that in a minute. And that's with the steel piston, how they're able to keep this thing light. Not only that, though, let me see if I can advance this picture. Yep, good. They did something completely different than had not been done in the light duty market. Now, keep in mind that they're pulling from, and when I design a part, a lot of engineers, a good engineer will take something that works in a good in an application that was used somewhere else, and then put it in a different application. It's been proven early on in another application. So this is a reverse flow engine, basically, where the exhausts obviously are on the inside and the intakes are on the outside, which is unconventional. However, it is completely conventional for things like 3500 series, Caterpillar engines. A lot of the industrial V12s, well, even back in you can go back and say a lot of the Caterpillar industrial application engines and some of the Waukesha's and different things like that were all reverse flow engines. And there's reasons for that, and that's because of the thermal advantage that it had due to heat losses. Obviously, combined gas law states that for every pressure, there's an equal and opposite temperature that can be related for this. So if you give me, any guys, some of the guys that are on or mechanics, everybody knows, like say 134. If you ever bothered to look at your PT chart, your pressure temperature chart on a 134 Freon while you're charging a vehicle, you notice that it was a 1-to-1 ratio. So for 1 pound of pressure, it would be 1 degree temperature. So you would notice when your Freon level on your low side starts approaching, starts inching downward to freezing, then obviously the evaporator starts freezing up. Well, I use that example because that's the combined gas law. So basically, you compress something, no different than your copper line coming off your air compressor. You go over and touch it after you've compressed it and it gets really hot, but there's you can actually take for that, and you can give a base pressure based off of the temperature that's on that and the volume around it. So it is basically a thermomechanical advantage because of the moving the heat from the exhaust closer into the closer to the turbocharger. We're not losing the heat that we so need to turn the compressor wheel. So it's much more efficient. Secondly, not just the efficiency of it, but also better throttle response. So we're able to pick up on that as well. So these were things that had not been done before. They were completely and radically different. They threw away everything that they had known. And while we're on it, obviously, just to state the obvious for those, again, this is going to be recorded. So I'm really not sure who's going to be listening to this later on, but we want to cover all the bases. And I can only assume that there may be some folks on the sales team that may not be diesel enthusiasts. So bear with me if I cover some very basic elementary knowledge, but I'm trying to appeal to all people here. But obviously the Ford 6-liter was plagued with 4 bolts per cylinder head. Again, that problem would be a patch fix for the 6.4, and a lot of guys wonder why the 18 millimeter, and I may cover some things in here that just may pique your curiosity. a lot of guys wonder why the 18 millimeter to the 20 millimeter switch. Well, the whole reason for that is so that you could actually incorporate the larger head stud because it was a tooling changeover that Ford was having. They wanted to increase the clamp load, and by doing so, if we can increase the diameter of the hold down fastener itself, the nut, then we can increase clamping forces and reduce the blown head gaskets. But it wouldn't truly get fixed and go back to the conventional 6 bolts per cylinder head that we have all come to know and love in the 7.3 liter and every engine truly that should have it. But they did that, and they fixed this with the 6.7. So those are some of the major things. They changed the way that the coolant flowed through the cylinder heads. It actually doesn't, typically your coolant flow on a cylinder head would go through the block first. So Ford didn't do that. Again, they did some really, really crazy things that were not anything short of truly. It was a very genius idea in some of the things they did with the 6.7. But the coolant crossover, that's the reason why you see the cylinder heads are quite different than what you would see on a conventional cylinder head like a 6.0 or 6.4 or 7.3, where the coolant would actually go through the block and then into the cylinder head. They did this so that they can adapt some of the front cover housing, the thermostat housings and the EGRs as well. So it made it more compact. Again, being able to lighten up a few things by being able to keep some of those things compact and condensed. So that was some of the stuff that they really had going on with the engineering just from the turbocharger side. But at the same time, they were really looking to try to increase the throttle response. And I do know that, obviously we're an engine remanufacturing company, and you might start asking yourself, well, you're basically given a tenure and a rundown of the 6.7. But if you don't understand the components that are going on in the engine, if you don't understand the things that are being bolted to it, you truly won't understand the reason why we do the things we do to fix the problems that we have. So you have to understand what chess pieces are on the board so that you can make the move. This is an early model turbocharger that everybody that has ever had these. There's two things they can say about them. Nothing sounds cooler than these early model turbochargers that were a dual plane turbocharger. And the other thing is nothing blows up faster after you tune it. They were a lot of fun until they weren't. They really sounded really, really good, but the problem with it is that the speed in which the turbo could easily be spun exceeded that in which the bearing could support. And the failure was inevitable on these turbochargers. So this is the first piece of evidence that I would submit to you on engine failures. Some of the things that you're going to see about the 6.7 liter, they have their own quirks and their own problems based off of the design change. And many times before, where you might be able to have a little bit more forgiveness with a grenaded turbocharger, especially when shrapnel is going through the inducer side of the turbo, you might not find your way through this large intercooler. A lot of times, because the intercooler, the way that it's routed, it would maintain and lodge in a corner of the intercooler. Now, this was changed drastically, I'll give you the second. I don't have a good picture of this, but I'll give you the second problem for the failure of this engine, and it applies directly to the turbo. Once this turbo grenades and it sends shrapnel into the intercooler, problem with it is this has changed drastically. It's no longer an air-cooled intercooler. It's actually water-cooled. Well, the passages are a lot faster and a lot less restricted. The problem with that is that when that turbo grenades, the chances of you putting metal or aluminum now on top of the piston have increased greatly because of the reduced amount of restriction in the design of that. Secondly, while we're already on the topic, this is not something that's totally uncommon. It's important to understand, especially as a sales team or especially as a sales team for your organization, you want to make sure that you're selling the customer a product that they're going to be happy with. But in order for them to be able to purchase from you in full confidence, you have to know a lot more about the product. And this, unfortunately, is not, this isn't a billet, coolant housing or something you can say, here, it's shiny, it screws on, righty-tighty, lefty-loosey, there you go. It's a lot more to it. So one of the things is to understand the failure of what that engine was going through before you go slapping another engine into it. Because a lot of times, more so with an engine, because everything bolts to it, an engine is subjected to whatever you bolt on it and whatever you pipe to it. So that can be failure through oil cooler. That can be failure through the way that you line up a transmission for the torque converter. But particularly while we're talking about the turbo, it is important to note that white smoke and bent rods come from one place. And typically, I would say almost one place only, but cracked heads. Matter of fact, before I jumped on this call, I had a phone call from a good friend and dealer of ours. And he had mentioned, I've got a customer that had hydrolocked an engine, and it was a 15-year model, I think it was. And I said, make sure when you go ahead and pull those heads, because we know what we do. I said, and that's just what we're here for, guys, is to support you. I said, make sure instead of slapping heads on because the head's cracked, and this is the reason why it hydrolocked, make sure that we, take and measure the piston protrusion, because I'll bet you anything that piston, the connecting rod's bent. Sure enough, he called me back and it was bent. So it could have easily been that the guy puts a set of cylinder heads on this guy's truck, gets it all back together, fires it up, and he's got low compression on one cylinder. And he's got a slight tapping noise in it because the rod's bent and it's hitting the block. So circling back around, the reason why I go through that is to tell you that it's extremely important to understand the cause of the failure. Intercoolers cracking is the number one, number two reason we see bent connecting rods, depending on the year model. But when the intercooler cracks, and it will, and we have seen it multiple times, obviously you're seeing white smoke, and a lot of these trucks out there no longer have emission components on them. And you're wondering, well, how in the world is coolant getting into the intake? Then you start panicking. You go, oh man, it must be the cylinder head. But there's ways around it to test it. Obviously, pressurizing the coolant system and isolating the intercooler would behoove you to do, so that you can make sure that before you put this engine on and you wind up having another failure, you definitely want to make sure that the components that you're installing are not the culprit. So because obviously water does not compress as it's going through the piston, it will not compress and it'll just bend the rod. Now there's reasons for that, which let me see. I'm as excited as you are to see the next slide. I haven't really looked through these that well. There's a couple of things about this. Now we're kind of going to, so geographically speaking, we're going to go through the engine one piece at a time, kind of starting from the north and working our way down. So you'll notice that these are two different rocker arm assemblies. One is a LC3Q and the other BC3Q as well. Now, one thing about that, if you look very close, you'll actually, and I think in the next slide, I'm looking down here, in the next slide, you'll actually see these are two different rocker arms, two different part numbers, and there's a reason for it. Now, the 6.7 has one big Achilles heel. Nobody ever talks about it, but it is there because most guys don't really, and we're fixing to see this problem a little bit more as we go downward in diagnosing the engine. One big problem that the 6.7, I don't know if I said 6.4, the 6.7 has is that oil pressure is a major issue with that engine. And there's reasons for that. And there's also reasons, while I'm on that topic, there's reasons that the 6.7, if you notice lately in the 2020 design, there's been a big change. And the change that has occurred is a different displacement oil pump. It is a variable displacement oil pump. The purpose of the variable displacement oil pump was strategic. It wasn't by accident. It was 100% on purpose because of problems that they're having. If you ever want to know what's failing on something, and I've said this 1,000 times in different webinars and different podcasts, if you ever want to know, just watch Ford's next year model. They're going to fix it. And they're real subtle about it because they don't want to issue a recall on something. But they're real slick in the way they fix stuff, and they'll slide a repair in. One of the things that we saw a lot on the earlier year models is the rocker arms actually falling off at idle. And the reason for this is obviously because of viscosity of the oil, the pour factor of the oil. Once we reach about 165, 170 degrees, the viscosity of oil absolutely exponentially decreases viscosity in a drastic rate. If you want to kind of test this theory, just put a oil pressure gauge on your truck, and you'll notice that when you see 170 degrees oil temperature, that at that point there's a lot of blends that are activated. but that oil will actually drastically drop off in pressure. So at idle, we see rocker arms actually just literally in some cases falling off. And what Ford did was they issued a completely different rocker assembly. Now it's very subtle in the design change, and I don't know that my cursor is actually going to show up for this. I may have this in a different picture, so let me go ahead and skip forward to the next one. Yeah, okay. So this is an updated rockers. Okay, they're actually, it says that they're using the same part number. I made this slide a long time ago, and I don't even remember all of the details on it, but so I'm kind of going back with it and seeing there's actually, yeah, I see it right there. There's a change in where that arrow is pointing. They extended that out so that if the rocker lost or the lifter lost oil pressure, it would not allow that rocker arm to lay over. It would stay on. So again, one of the big things that they changed too on this is keep in mind that they were running a 5W oil on the earlier year models. The purpose for the 5W oil mainly was for emissions and fuel mileage. So I know I said emissions twice, and there's a reason for that. The reason why you can help emission systems greatly by reducing the weight of oil is pretty simple. So anything that we get in, which will, this can go into a whole nother topic, and I apologize, but the topic being the change in oil in 2017, we really saw a major change with the zinc dichlordithium phosphate that was actually put inside the oil. And it changed from 1,800 parts per million in some cases down to just a few hundred parts. Now, the major change for that was because of the emission systems that these manufacturers were faced with. Now, that being said, when you have a lighter weight oil, it sheds off the cylinder wall a lot easier. The heavier weight oil will actually retain on the cylinder wall, and the ring sometimes will not wipe as thoroughly as it does. Now, there's a couple of reasons. For one, that is if we get any oil that's in the combustion chamber left and it burns, it's going into the diesel particulate filter, and that can all lead to premature failure of those components. Also, fuel mileage through reduced resistance against the lower portion of the engine through the vane bearings and rod bearings, we can decrease some of the parasitic loss that we're seeing on the engines. Now, that being said, they also, because of this, were running 8/10 clearance. Okay. So there right out of the gate, we were seeing a tremendous amount of failure. Now, I know geographically speaking, and I'm kind of getting out of order here, but I have to talk about it right now because we're talking about oil pressure and rocker failures. But anyways, they were seeing a lot more failures. And if you start tracking this as we do, because the core fallout is a real big problem on 6.7 Powerstrokes. We had a very large manufacturing facility come in and actually won't mention any names, but they came and they spoke to me about this particular platform. They wanted to remanufacture this for a very, very, very large person. And so we're talking about core fallout. And if you track the cores, you'll note that you'll get more spun mains off of the vehicles that are actually up north. And there's a reason for that. A couple of reasons. Why is a lot of these engines are being ran on a 15W oil, and up north, that oil will absolutely, the pour factor of the oil being a heavier weight, will move extremely slow. Now, again, there has to be another thing that has to be said for that, and we'll kind of dial that in a minute. The 6.7 had further to go to pipe that oil, and it actually had a larger volume to fill up before it ever got to the first bearing. So that was a lot of the issue there. They piped that oil from a long ways away, and we'll look at that in a minute. While we're on the subject of cylinder heads, this is a steam cleaned. If you do any tacking on these trucks, if I got any dealers out there, this is a site that you probably have seen before. Cracked cylinder heads where it looks like it's steam cleaned. You can actually see the crack in this picture. And so obviously the problem with it is that if, you could hydraulic a 6-liter, you can, honestly, they're very resilient engines. You can get away with a lot with a 6-liter connecting rod, a lot more than you can with a 6, especially an 11 to 16 connecting rod. If I've seen those trucks guys forget to, well, they don't forget to, but they don't torque the injectors down properly, fills the cylinder up with fuel, and this thing goes knocking, and you get the problem resolved, you get the injector seated and everything. And still, you've got an engine that will run and last. You can't get away with that with an 11 to 16. And there's a reason for that. Again, when we first jumped on the call, what we were talking about was what we wanted was a very lightweight engine. We want this thing to be a diesel that your grandmother wouldn't mind driving. It has to have really good throttle response and be extremely smooth. There are some give and takes to that, though. And that is, you'll find in the connecting rods. This is another failure that is probably, I guess this is, I would say probably the most talked about failure that we see in the 6.7. Biggest problem, hands down, especially with the early year model trucks. 11 to 14s really were plagued with this, especially the early 11s, but they still, nonetheless, they did have an issue with the valve failure. Initially, when they came out, it was so problematic. They initially thought that it was the glow plug that was causing the failure, and then once the glow plug was pinned between the valve and the seat, that it actually would damage the valve itself, but that's not the case at all. The chicken or the egg, which came first, the problem with it was the valve failed through intense heat that was being subjected to it. And you'll typically see these types of failures on trucks that are high duress, and not always. I mean, if guys pulling campers and F450s, F350s, we see more failures out of a 1.5 ton trucks and stuff like that. Or guys that have tuned, DPFs being stopped up, anything that's going to cause excessive heat. Now, I often give the example of if you took a pin off your desk and you held it up in the air and I asked you, is it heavy? You'd say absolutely not. And then if I said, okay, well, great, hold it there with your arm straight out for the next 8 hours. I'll be back and I'll check in with you. Is it going to be heavy when I get back? You'd say, absolutely. My arm's wore out. I mean, the arm itself's wore. I can't hold that up. So it's not the weight of something. It is the duration and time in which you have to hold it. Okay, so people ask all the time, how many EGTs are too high? Well, it's not the actual EGT that's the problem necessarily, but most of the time it's the duration in which the components will be heat soaked. The same thing in this particular failure, as you can start seeing the area, and I don't know if you can actually start seeing this is very reminiscent of a blowtorch that's actually happening. So you'll start to see that the valve starts cracking, and as this pressure is going through that crack, it looks just like if you were to take a blowtorch and start to cut away with that valve. The heat in certain applications where guys are going up a long grade, we see this in Cummins all the time. The valve seat's failing, and the valve seats will fail. It doesn't matter really what you do if you're running outside the parameters in which it's made to operate. So this failure is pretty common on these, and we see this pretty often. That for this reason, we will not use any OE valves back in these cylinder heads. For that very cause, we've upgraded the valves so that they can withstand more heat. But there again, it's extremely important. A lot of tuners out there, guys pulling heavy, and if they heat soak anything, there again, it goes back to that same illustration of having an extended amount of time where something can absorb that heat. And keep in mind, when it does absorb the heat, and the metal has memory to it. It never goes back to the original condition in which that it was designed. And we see this in valve seat failures when guys go, I talked to a guy not long ago that had a Cummins failure on a cylinder head. And I said, I bet you're probably pulling up a long hill, got heavy load. It was a 5,500 truck with a Race Me tuner on it. And he said, well, no, we were actually on flat ground, but you're right. We're in West Virginia and we pull up, we service these coal mines all the time. And you're right. This is, we did have that. I mean, we do pull heavy. It is a 5,500. It does get really hot. And we have had this failure before. And so the issue with it is that being able to monitor those things and defueling there's no replacement for that. But heat soaking that valve seat again and again and again, eventually that 4 to 6 thou press fit on a cast iron head or 6 to 8 thou press fit on an aluminum head, eventually it's not going to retain that shape and it will come out. It can only withstand so much duress. So that's your valve failure. This is the leftovers of when it goes to pound town against the cylinder head and the piston itself. There's not a lot left there, and it just really makes a big mess. Now this actually was a valve seat failure. No, excuse me, I can see it now. So you can see right over here the missing part of the valve where it split. So as it got hot, it began to split, and again that blowtorch effect took place, and it's pretty common problems with this. Dual lash adjusters. A lot of the problems, again, guys that would complain about the lifter failure. Not so much of a problem with the actual lifter. This is completely redesigned lifter that they came back with a larger axle, much larger roller. The lash adjusters are 1-inch 172. The one before its predecessor was a 902, I believe it was. I wrapped up. No, I think it was a 918 or 920. So a lot larger lifter itself. So that's a major change in this. We really don't see a lot of lifter failures. I know that there are some out there, and guys have had this, but typically when you start seeing lifter failures, that's because oil temperatures are increasing to a point at which you start having fluid film breakdown. And now no longer this oxidation that occurs in the oil no longer can provide the protection needed for the bearings, which the needle bearings are the fastest moving bearing now in the whole engine off the lifter. This is a microstructure, and it basically is a breakdown. It shows you the nodularity of the compacted graphite iron. This is quite different than what you would see on a gray cast iron block. So it is a lot more dense material when it comes to the compaction of the microstructures. So that's what makes it much stronger. There are some things though that are about this quite differently in the way that it machines and the machining processes that are used for this. A lot of PCD is used for the machining processes, and I won't go too deep into that for the compacted graphite iron instead of typical carbide or CBN, cubic boron nitride. There's some advancements that have been made, but some of the biggest challenges are surface finish and waviness on the CGI blocks. It is extremely important, and that's the reason why we measure with profilometers, not just the surface finish, but then also coming back and measuring through testing through Fujifilm, which is basically a piece of paper that you would compress two objects with, check the clamp load to find out if there is any adverse things going on between the two mating surfaces, which is extremely important to stay on top of when you're dealing with this. Now this goes back to the connecting rods. Okay, so here we have a 6-liter rod on the bottom, so you see a lot larger cross-sectional area. The one above that is 2017 to 2019, and the one below that is an 11 to 16. So there's basically 5 connecting rods on a 6.7 liter that they came out with. The top one, the original, and then they had the hybrid rod, which is 16 and a half. So they changed the wrist pin design from a 34 millimeter to a 35 millimeter when they went to the 17 to 19. But again, kind of like that 18 millimeter to 20 millimeter transition, that's the reason why they had the hybrid rod. You would have thought that it would have just been easier for them to make the jump, but typically the reason why that is because the piston manufacturer, they can't get stuff together at a certain time. There's a lot of things. If you've ever built a house, it's almost kind of the same way. You're trying to orchestrate all the contractors on something. So sometimes there's some overlap in different things, and that's the reason for this 35 millimeter in that insufficient, we'll call it rod, the 11 to 16. So it's extremely reminiscent of the 6-liter rod, much more robust, larger cross-sectional area, holds more power, not nearly as problematic when it comes to the bending that they were seeing. While that's on, I'm going to bear with me here because I'm going to back up just 1 minute. I got my pictures out of order, so I'm going to click back through here. So yep, there we go. Okay, all right. This is some interesting information for you guys out there because we offer steel piston upgrades, and there's a lot of guys out there that are doing steel piston upgrades, and we were guilty initially through testing. Most of the guys Ford was having a lot of problems with the 6.7s, trying to get that product out. They still are. There's a tremendous amount of shortage on the 6.7s. So what a lot of guys are doing, and I'm going to get into this in a minute, but a lot of guys are taking a 2020 block, and they have a rotational assembly and everything in there of the steel piston, and they're putting it into the to the older engines. And there are some things about that. Most people go, oh yeah, it's fine. You're going to change your front cover. You're going to change your cylinder heads. You're going to change your crossover tube. You're going to change your upper and lower oil pans, but you can use the short block. Well, actually, you can do, a dog can walk on its hind legs. It's not natural, and it's not going to last for very long, but it's the same thing with the 2020 blocks. What we noticed was 30% or more oil pressure loss by doing that. By using a Eurotor style pump with the with the new blocks, you will see a difference of 30% of pressure drop cranking on startup. That's a big problem. That's the reason why they changed that pump design, because the galley diameters have changed, and some things about the block itself are no longer the same. So that being said, we do offer that steel piston upgrade, it actually comes up with it's basically a sleeve block now, which is an upgrade. It's nice, but it does add, it has a lot of work to be able to do that. We could do it the old way that we were doing, but the problem with it is, again, oil pressure is sorely sacrificed on that. Now, in this photo, you're going to see 3 different connecting rods, 3 different pistons, 3 different wristbands. One thing that you're going to note, though, that's interesting about this is that the 11 to 16 rod that we were looking at, talking about a minute ago, on the far right, 2,332 grams. The one on the left uses the same piston, but is now a 35 millimeter rod. If you look at the wristbands, you can actually see the whole difference on that. So again, it's that larger wristband. You're seeing some things change. This is a 2,314 grams difference. So there were some things that they did in that they took out material on that rod a little bit and lightened it up. But the weirdest thing about it all is you got a steel piston in the middle, and that steel piston is actually lighter than both of them. And the reason why is that they actually moved the wrist pin up further into the piston itself, so close to the, and I'm going over some of these things, so the performance gains on our workhorse model, you'll see, and I wish I had a cross-sectional picture of this piston, but the top ring land is about somewhere in the range of about 3 millimeter or less from the top of the piston. This does not leave room for any machining. There is companies out there that will actually, crazy enough, they're machining some valve reliefs on that 6.7 piston. It's certainly not recommended. It will ultimately lead to failure. But that piston right there is quite a bit lighter as far as the grams of the connecting rod, the wrist pin. And this is primarily done because even though it being a steel piston, they've reduced the amount of skirt area there, and they've also reduced the wrist pin area. So let me get back here to where we were, and bear with me one second. Big issues here. Now, this is something that's really important to talk about. There's a couple of different gaskets designs. I think there's 3 total that they actually came out with. This one actually uses a gasket. So the earlier year models, they were using a different way to seal. Later on in the 2017s, they changed, I believe, this gasket on here. I could be wrong on that, so don't quote me on it. Now, the purpose for the problem, or the reason for the problem, is not what most would think. Where we see these leaks occur is primarily because people, and not always, this is not primarily, let me rephrase that just a second. The torsional load that's being placed on the back of the engine, okay, or the radial load, I should say, not the torsional, but the radial load, what happens is that when you take off, if you've ever watched a big truck take off from a red light, obviously you start seeing the torque factor take place and the frame twist. The twisting effect on this particular engine, because the rear cover, the bell housing area and the upper oil pan are integrated together, it puts a tremendous amount of stress in that between the 2 mating surfaces there. What we've seen quite often is that leaks develop when guys are removing or not making sure the dowel pins are located properly into the rear area of the engine on this upper oil pan, and also if the transmission's not torqued properly. If the transmission is not torqued properly, it allows it to pry like a vise, or excuse me, like a kind of like a seesaw, but it pries against that upper oil pan, and it sorely increases the failure rate of these seals that are around the top and the adhesive. So it's extremely important when they're installing these things to make sure that they torque the transmission back. Nobody uses a torque wrench when they're installing a transmission. I don't know that I've ever seen, hardly a guy, very few times ever, if ever, hardly, torque a transmission back in with a torque wrench. So what they typically do is they stick it up there and they run it in with their hand. They pop it with a 3/8 impact because it's small enough to get there, and they'll come back and they'll just kind of snug it up a bit. But they don't check all the way around again a lot of times. And as this transmission is getting loose, like I say, now no longer, especially if there's a dowel pin that's missing on this thing, it will lead to problems, and it'll be quite a headache with oil leaks. Now, the reason for this picture is because I want to show you guys, this is obviously the oil cooler side. I've got a little teaser here. We've got a part that's coming out that that's got some really, it's going to be very, very helpful for these guys that are towing and stuff. So keep a lookout for that. This oil passage that's going across the oil pan, the upper oil pan. To understand the problems of the 6.7 liter engine, you have to understand the oil routing. So the way the thing works is that oil gets picked up from originally the gerotor style pump, and excuse me, as it was picked up through the pump, it would go through the upper oil pan. It would go into the oil cooler, out the oil cooler, across the block, through the oil filter housing, back, through the filter part of the oil filter, and then it would go into the block, and then it would take a hard 45-degree turn, and then from there it would hit a hard 90, and it would have some oil that would feed the lifter galley on one side, some oil that would actually go. Now the camshaft's quite a bit different. I don't know if I got a picture of that or not, but I'm looking to see. Nope, I don't. So the camshaft's quite a bit different. Most camshafts are oiled from the outside in, not from the inside out. So what happens is that this oil galley feeds the camshaft, and it fills this long tube. Okay, this is the reason why it's absolutely important for these guys to pre-lube the engine. If they don't, it's going to take forever and a day for oil to get where it needs to go. It's extremely important on a 6.7. You could get away with it on a lot of the other engines. However, that being said, you still were causing wear on the oil pump if you don't pre-lube it, and most folks don't. But anyway, it has to fill up the whole entire tube of the camshaft. And the way that it works is on the number 5 journal, that's the fill hole, we'll call it. And it fills the camshaft up, and then it oils from the outside in. Now, if the remanufacturer doesn't do their job and get rid of the plug that's in the back of that, and go and thoroughly clean that camshaft out with some type of rifle brush or something along that nature, you're going to have all that contamination that actually just kind of, it congregates in the camshaft and will cause failure. And we have seen guys before that have had cam bearing failure. Not often, but it can happen because this is kind of where all the garbage, like I say, it tends to congregate there. And then once it comes through the camshaft and it oils from the inside to the outside, it actually passes through and oils the main bearings on the other side, and also oils the lifter galley. So it just has a lot to contend with the whole problem with oiling. This is a common problem. Well, I wouldn't say this is a common problem as much as the Duramax, but it is seen sometimes on the 6.7 Powerstrokes, especially the pre-15 and down. The reason for it is because, and typically when you wind up seeing any type of failure on any type of crankshaft of the Duramax and the Powerstroke, you'll typically find it after the number 1 throw. And the reason for that is there is a tremendous amount of orbiting that takes place because the harmonic balancer is designed to act as a torsional shock absorber. So when you ring, if you were to hit a tube and it starts ringing, you place your hand over the tube. The frequency it's vibrating at, the intensity that it's vibrating at. As soon as you place your hand upon it and you grab it, it immediately, it quits ringing. No different. That's just the most simplistic way of explaining the job of a dampener. Now, there's two forces that are acting against it. The first order imbalance and the second order of imbalance. But what we're dealing primarily here with is the first order of imbalance. Now, that being said, they had tried to lighten this thing up as much as they possibly could. And we talked about this earlier. One of the things that they tried to lighten up was the harmonic balancer. By doing so, there was not enough mass. And they subtly changed something without bringing a lot of fanfare to it, a lot of notice to it. They subtly changed the harmonic balancer. And in 15, they drastically changed it to a much heavier shock absorber, we're going to call it. And so we no longer really saw the crankshafts breaking unless there was an oil pressure issue. So this is the crank dampener off of an 11. This is a crank dampener off of a 15. You see that there's a drastic difference in the casting design, the windows that are in it. Anybody that's worked on these things very long on the earlier year models knows how much difference there actually is. We don't use an 11 dampener on anything. All of our stuff supersedes to the later part number so that we do not have these problems. That is pretty much the whole bottom end failure. Now I'm going to back up to one more thing. Now keep in mind this whole presentation was done a good long while ago, and since then there's been a few more things that we found. This is a really important picture, and the reason why it's a really, really important picture is because it tells a story of oil pressure and what happens in oil pressure. There's a dirty little secret that I'm going to let you in on it. And in remanufacturing and aftermarket parts, as people know, a lot of times aftermarket parts are not held to the same standard. In ISO 9001 standard of the facility that they're built in, or the parts themselves are not held to the same standard in testing that the OE was. Now, the way that it works is the cam bearing. There's two manufacturers basically that make these cam bearings. There's Ford, and then there's the other people. Now, Ford is different because the way they make the cam bearing, they actually will put the cam bearing in and then they'll line bore it in place. There's a reason for this. The reason why is because of the cam tunnel it's a barrel of snakes. This thing is as crooked as it can be. Okay. And so they don't really chase it. They're not going to try to really make sure that, because you have so much core shift in castings, there's no real good way for them to ensure by boring this that it's going to maintain that position. So they put the cam bearings in and they bore them in place, and that's how they make sure that the camshaft is running true. The other guys, well, if they kept it true 2000s tolerance in the cam tunnel, problem with it is that straight edge that you're seeing on there, if it's flipped upside down, there are some engine blocks, and there are many actually engine blocks that will come in, and you'll see 1000s, 2000s deviation in that cam tunnel. Now, how are they going to sell a product? By knocking the bearings in, and they're going to get a lot of phone calls, because if you go, okay, this is a 2000s clearance, right? Now keep in mind 2000s is 2/3 of the human hair. Okay, so if we sell this cam bearing and it's supposed to maintain a 2000s clearance against the cam journal, which for whatever, I can't remember the value of it, doesn't matter. But the issue is that we're not only dealing with a 2D plane, so to speak. We're dealing with 5 different journals that this thing has to go through. That means that if one journal is offset to one side, no longer will you have a 2000s clearance. Now you're actually trying to put something that's very straight into something that's very not straight. And what will happen is that 2000s will not be sufficient for you to get cam to go all the way through the block. Well, they have a fix for that, and they open up the clearances immensely. Okay. I've seen clearances of 8,000s on some of these bearings. It's insane. And it's common practice. There's only one reason why we found out about this, because Cam bearings are something that most people just, they install it, it fits, it goes, enough said, right? Now, a lot of people take the time to look into this. We do. And the reason why we do is because we value our customers and we value the product that we put out. So what we wound up doing and finding out was, is that if you machine these to 2000s and you drive them in, some blocks will work, some blocks won't work. And the way that you'll see again about a difference of 5 pounds of oil pressure by using the aftermarket cam bearing that is typical. Again, you can't use the forward bearing because it will not fit unless you line bore the entire thing, and most people don't have the capability of doing that. So what we do in house is we actually machine our bearings to fit, so that we can line hone it, we can straighten it out, and then we can machine the bearing to fit. This way we can achieve about another 4 or 5 pounds of pressure that is absolutely imperative for the 6.7. So that makes our engines last longer. That makes our valve train noise go down, it's reduced. I mean, there's a lot of benefits, obviously, that go with that. So those are a few things to kind of touch on. I know that I'm long-winded on this thing, but I know that it was being recorded. So I wanted you guys to be able to see that. There's one last thing, and then I'm going to finish with this and turn it back over to Adam, if I can find it. Everybody knows about the failure of the cam gear. This is really problematic. Anybody ever work on these things too long, you'll find that you got 32 bent push rods. And the reason for the 32 bent push rods is pretty simple. The cam gear spins. There's actually no dial that lines this thing up. It's put in a fixture from the factory, and it's in a lineup tool. They heat it and they press it on, and that's it. The problem with that is if that gear ever moves for whatever reason, because there's a lot of things that go on more than a press fit. It's the surface finish. It's the roundness. There's a lot more things to consider than what most people think a press fit is. Just, you measure in 2 points and you drop it on. Surface finish plays a big role in that. So there's a lot of things that can affect that. We don't want to have those problems, and we don't have those problems. And the reason why we don't have the problems is because the gears are TIG welded. So that eliminates any future failures, any problems that could exist. So that being said, I'm going to turn it over now to Adam at this time, and I will stop sharing my screen.
All right. Thanks, Cass. Real quick, Cass, before you go away, anybody have any questions about, everything that Cass shared? Anything your customers have asked you that you're curious about? Or I have muted everyone, but you can unmute yourself. Nope, cool, nothing. Anything comes to mind, obviously email us. I wanted to recap. So obviously we're making the 6, 7, and 4 different performance packages, just based on what you need, what your customer needs. Also short block, long block, full runners. So you can get each of those packages in 3 different ways. You can also get the heads that way as well. We have brand new heads and remanufactured heads in a stage 1 or a stage 2. Next week, we're going to be talking about the 6.4. So same webinar essentially, just with the 6.4. Go down all the problems and fixes we have for it. Something else we should have done by next week is going to be our dealer portal. If not, it'll be later in the week. But all of these recordings, so we were recording this, will be on that dealer portal, so you can go back at any time. As well as any sales materials, our catalog, any of our one sheets, load sheets will be there eventually as well. All sorts of links to any other videos we have on our products. Basically, just trying to put any little bit of information we can in there to help you out. All right, guys. Well, we appreciate it. Hope to see you guys next week. Have a good week. Thanks, guys.